Okay, so let's start with the third and the final tutorial on deep learning. So deep learning is a subset of machine learning, as we already discussed, where artificial neural network algorithm inspired by the human brain learn from large amounts of data. Deep learning allows machines to solve complex problems even when using a data set that is very diverse, unstructured and interconnected. Type of deep learning network, there are a number of neural network topologies. Some of them are perceptron. The perceptron model is also known as a single layer neural network. The neural net contains only two layers, that is input layer and output layer. In this type of neural network, there are no hidden layers. It takes an input and calculates the weighted output for each node. Afterwards, it uses an activation function, mostly a sigmoid function, for classification purposes. Applications in this is classification, encode database, that is multi-layer perceptron, monitor access data, multi-layer perceptrons. Feed forward. A feed forward neural network is an artificial neural network in which the nodes do not ever form a cycle. In this neural network, all of the perceptrons are arranged in layers where the input layer takes in input and the output layer generates output. The hidden layers have no connection with the outer world. That is why they are called hidden layers. In a feed-forward neural network, every perceptron in one layer is connected with each node in the next layer. Therefore, all the nodes are fully connected. Applications in this are data compression, pattern recognition, computer vision, sonar target recognition, speech recognition, handwritten characters recognition. Now, radial basis network, RBN or radial basis function networks are generally used for function approximation problem. They can be distinguished from other neural networks because of their faster learning rate and universal approximation. The main difference between radial basis network and the feed-forward network is that RBNs use a radial basis function as an activation function. A logistic function, sigmoid function, gives an output between 0 and 1 to find whether the answer is yes or no. The problem with this is that if we have continuous values, then an RBN can't be used. RBI determines how far is our generated output from the target output. These can be very useful in case of continuous values. In summary, RBIs behave as FF, that is feed forward network, using different activation functions. Applications of this: function approximation, time series prediction, classification, system control, etc. Now, deep feed forward. A deep feed forward network is a feed forward network that uses more than one hidden layer. The main problem with using only one hidden layer is the one of overfitting. Therefore, by adding more hidden layers, we may achieve, not in all cases, reduced overfitting and improved generalization. Applications of this is data compression, pattern recognition, computer vision, ECG noise filtering, financial prediction, etc. Now, RNN, that is recurrent neural network. Recurrent neural networks are a variation of feed-forward network. In this type, each of the neurons in hidden layers receives an input with a specific delay in time. We use this type of neural network where we need to access previous information in current iterations. For example, when we are trying to predict the next word in a sentence, we need to know the previously used words first. RNNs can process inputs and share any length and weights across time. The model size does not increase with the size of the input, and the computations in this model take into account the historical information. However, the problem with this neural network is slow computation speed. Moreover, it cannot consider any future input for the current state. It cannot remember info from a long time ago. Applications in this is the machine translation, robot control, time series prediction, speech recognition, speech synthesis, time series anomaly detection, rhythm learning, music composition, etc. Long short memory, long short term memory, LSTM. LSTM network introduce a memory cell. They can process data with memory gaps. We can notice that we can consider time delay in RNNs. But if our RNN fails when we have a large number of relevant data and we want to find our find out the relevant data from it, then LSTM is the way to go. Also, RNNs cannot remember data from a long time ago. In contrast to LSTMs, applications for this is speech recognition and writing recognition. Gated recurrent unit, that is GRU. Gated recurrent units are a variation of LSTMs because they both have similar designs and mostly produce equally good results. GRUs only have 3 gates and they do not maintain an internal cell state. Update gate determines how much past knowledge to pass to the future. Reset gate determines how much past knowledge to forget. Current memory gate is subpart of the reset gate. Applications of this is polyphonic music modeling, speech signal modeling, natural language processing, etc. Autoencoder. Now this is also coming up in a big way now. An autoencoder neural network is an unsupervised machine learning algorithm. In an autoencoder, the number of hidden cells is smaller than the input cells. The number of input cells in autoencoders equals to the number of output cells. On an AE, that is autoencoder network, we train it to display the output, which is as close as the fed input, which forces autoencoders to find common patterns and generalize the data. We use autoencoders in the smaller representation of the input. We can reconstruct the original data from compressed data. The algorithm is relatively simple as autoencoder requires output to be the same as the input. Encoder convert input data into lower dimensions and decoder can reconstruct the compressed data. Applications in this is classification, clustering and feature compression, etc. Variational autoencoder. A variational autoencoder uses a probabilistic approach for describing observations. It shows the probability distribution for each attribute in a feature set. Applications interpolate between sentences, automatic image generation, etc. Denoising autoencoder, DAE. In this autoencoder, the network cannot simply copy the input to its output because the input also contains random noise. On DAE, that is denoising autoencoder, we are producing it to reduce the noise and result in meaningful data within it. In this case, the algorithm forces the hidden layer to learn more robust features so that the output is a more refined version of the noisy input. Applications: feature extraction and dimensionality reduction. Sparse autoencoder, SAE. On a sparse autoencoder network, we would construct our loss function by penalizing activations of hidden layers so that only a few nodes are activated when a single sample when we feed it into the network. The intuition behind this method is that, for example, if a person claims to be an expert in subjects A, B, C and D, then person might be more of a generalist in these subjects. However, if the person only claims to be devoted to subject D, it is likely to anticipate insights from the person's knowledge of subject D. Now, applications for this is feature extraction, handwriting digits recognition, etc. Markov chain, MC. A Markov chain is a mathematical system that experiences the transition from one state to another state based on some probabilistic rules. The probability of transitioning to any particular state is dependent solely on the current state. and time elapsed. For instance, some set of possible states can be letters, numbers, weather conditions, baseball scores, stock performances. Applications: speech recognition, information and communication system, queuing theory, statistics, etc. Hopfield network (HN). In a Hopfield neural network, every neuron is connected with other neuron directly. In this network, a neuron is either on or off. The state of the neurons can change by receiving input from other neurons. We generally use Hopfield network to store patterns and memories. When we train a neuron network on a set of patterns, it can then recognize the patterns even if it is somewhat distorted or incomplete. It can recognize these complete pattern when we feed it with incomplete input, which returns the best guess. Applications: optimization problems, image detection and recognition, medical image recognition, enhancing X-ray images, etc. Boltzmann machine (BM). A Boltzmann machine network involves a learning a probability distribution from an original dataset and using it to make inference about unseen data. In BMs, there are input nodes and hidden nodes. As soon as all our hidden nodes change its state, our input nodes transform into output nodes. For instance, suppose we work in a nuclear power plant where safety must be the number one priority. Our job is to ensure that all the components in the power plant are safe to use. There will be states associated with each component using Boolean or simplicity 1 or usable and 0 for unusable. However, there will also be some components for which it will be impossible for us to measure the states regularly. Furthermore, we do not have data that it tells us that the power plant will blow up if the hidden component stops functioning. So in that case, we build a model that notices when the component changes its state. So when it does, we will be notified to check on the component and ensure the safety of the power plant. The applications are dimensionality reduction, classification, regression, collaborative filtering, feature learning, etc. Now, restricted Boltzmann machine. We have seen BM and now we are learning RBM, that is restricted Boltzmann machine. RBMs are a variant of BMs. In the model, neurons in the input layer and the hidden layer may have symmetric connections between them. One thing to notice is that there are no internal connections inside each layer. By contrast, Boltzmann machines may have internal connections in the hidden layer. These restrictions in BMs allow efficient training for the model. Applications: filtering, feature learning, classification, risk detection, business and economic analysis, etc. Deep Belief Network (DBN). Now, deep belief network contain many hidden layers. We can call DBNs with an unsupervised algorithm as it first learned without any supervision. The layers in a DBN acts as a feature detector. After unsupervised training, we can train our model with the supervision methods to perform classification. We could represent DBNs as a composition of restricted Boltzmann machine and autoencoders. Last DBNs use a probabilistic approach towards its results. Applications are retrieval of documents, images, non-linear dimensionality reduction. Now, deep convolution network (DCN). Convolutional neural network or neural network used primarily for classification of images, clustering of images, and object recognition. DNNs enable unsupervised construction of hierarchical image representation. DNNs are used to add much more complex features so that it can perform the task with better accuracy. Applications are identify faces, street signs, tumors, image recognition, video analysis, NLP, anomaly detection, drug discovery, checkers game, time series forecasting, etc. Neural network, neural network are convolutional neural network that work in a reversed process. Even though a DN is similar to a CNN in nature of work, its application in AI is very different. Deconvolution networks help in finding lost features or signals in networks that deem useful before a DN may lose a signal due to having been convoluted with other signals. A deconvolution network can take a vector that make a picture out of it. Applications for that is image super resolution, surface depth estimation from an image, optical flow estimation. Now, deep convolutional inverse graphical network, that is DCIGN. Deep convolution inverse graphical network aim at relating graphics representations to image. It uses the elements like lighting, object location, textures, and other aspects of image design for very sophisticated image processing. It uses various layers to process input and output. The deep convolutional inverse graphic network uses initial layers to decode through various convolutions, utilizing max pooling, and then uses subsequent layers to decode with unspooling. Applications for this is manipulation of human faces. Now, generative adversarial network GAN or GAN. Given training data, GANs learn to generate new data with the same statistics as the training data. For example, if we train our GAN model on photographs, then trained model will be able to generate new photographs that look authentic to the human eye. The objective of GANs is to distinguish between real and synthetic results so that it can generate more authentic results. Applications: generate new human poses, photos of emojis, face aging, super resolution, clothing translation, video prediction, etc. Liquid state machine, LSM. A liquid state machine is a particular kind of spiking neural network. An LSM consists of an extensive collection of neurons. Here each node receives input from an external source and other nodes, which can vary by time. Notice that the nodes on LSMs randomly connect to each other. In LSMs, activation functions are replaced by threshold levels. Only when LSMs reach the threshold level, a particular neuron emits its output. Applications for that is speech recognition and computer vision. Now, extreme learning machine, that is ELM. The major drawbacks of conventional systems for more massive data sets are the slow learning, speed based on gradient algorithms, tuning all the parameters iteratively. ELMs randomly choose hidden nodes and then analytically determine the output weights. Therefore, these algorithms work way faster than the general neural network algorithms. Also, in extreme learning machine networks, randomly assigned weights are generally never updated. ELMs learn the output weights in only one step. Applications for this are classification, regression, clustering, sparse approximation, feature learning. Now, eco-state network, ESN. Now, this eco-state network is a subtype of recurrent neural network. Here, each input node receives a non-linear signal. In ESN, the hidden nodes are sparsely connected. The connectivity and the weights of hidden nodes are randomly assigned. On ESNs, the final output weights are trainable and can be updated. Applications like time series prediction, data mining, etc. Deep residual network, DRN. Deep neural networks with many layers can be tough to train and takes much time during the training phase. It may also lead to degradation of results. Deep residual network DRNs prevent degradation of results even though they have many layers. With the DRNs, some part of the inputs pass to the next layer. Therefore, these networks can be quite deep. It may contain around 300 layers. Applications for this is image classification, object detection, semantic segmentation, speech recognition, language recognition, etc. Now, Cohen networks, KN. A Cohen network is an unsupervised algorithm. Cohen network is also known as self-organizing maps, which is very useful when we have our data scattered in many dimensions and we want it to in one or two dimensions only. It can be thought of as a method of dimensionality reduction. We use Cohen word network for visualizing high dimensional data. They use competitive learning rather than error correction learning. Various topologies, rectangular grid topology, hexagonal grid topology, and applications for them is dimensionality reduction, assessment of prediction of water quality, coastal water management. Support vector machine, SVM. The support vector machines neural network is a hybrid algorithm of support vector machines and neural networks. For a new set of examples, it always tries to classify them into two categories, yes or no, 1 or 0. SVMs are generally used for binary classification. These are not generally considered as neural networks. And applications for these is face detection, text categorization, classification, bioinformatics, handwriting recognition. Neural tuning machines, that is NTM, a neural Turing machine architecture contains two primary components, neural network controller and memory bank. In this neural network, the controller interacts with the external world via input and output vectors. It also performs selecting read and write, that is R/W operations by interacting with the memory matrix. A Turing machine is said to be computationally equivalent to a modern computer. Therefore, NTMs extend the capabilities of a standard neural network by interacting with the external memory. Applications for this is robotics and building in an artificial human brain. So this completes the deep learning. Thank you.